When molded pulp operations struggle with inconsistent part quality, rising scrap rates, or unexplained downtime, attention often turns to upstream variables like furnish composition, vacuum settings, or forming pressures. What's frequently overlooked is that woven wire mesh screens record these issues in real time. Wear patterns, thinning, and localized damage are physical responses to system behavior. In molded pulp and fiber applications, woven wire mesh sits at the intersection of flow, fiber, and vacuum. As pulp moves across the screen, process imbalances show up first on the mesh surface. Areas experiencing excessive abrasion, premature corrosion, or irregular loading point directly to upstream issues long before they trigger alarms or quality failures. Woven wire mesh wear in molded pulp systems is rarely uniform, and that unevenness is a valuable clue. Different wear patterns form based on how fiber, water, vacuum, and chemistry interact with the screen's surface. By understanding these patterns, operators can use mesh as a reliable process indicator. First, there's localized abrasion. Thinning or polishing in specific zones points to mechanically driven causes such as elevated flow velocity, directional slurry movement, or fiber bundles repeatedly contacting the same area. It can also indicate uneven furnish dispersion, where coarse fibers or contaminants impact specific regions rather than distributing evenly. Then there's also uniform thinning. Smooth wear across the entire mesh surface suggests global operating conditions rather than localized mechanical issues. Higher solids loading, extended runtimes without adequate cleaning, or elevated forming pressure gradually reduce wire diameter over time. Accelerated uniform thinning indicates that forming parameters are being pushed beyond design limits. Then there's chemical-driven wear. Presenting as pitting, discoloration, or surface roughness rather than smooth abrasion, chemical wear occurs when stainless steel mesh faces aggressive pH conditions, oxidizing agents, or harsh cleaning cycles. This alters the wire's surface texture, reducing drainage and efficiency and fiber release even before significant mechanical thinning occurs. And finally, there's edge and transition zone damage. Broken wires at screen borders or attachment points typically reflect stress concentrations. Repeated failures in these identical locations signals excessive vibration, pressure cycling, or mechanical misalignment elsewhere in the system. When elevated with process conditions in mind, these distinct wear mechanisms turn the mesh into a readable map of upstream conditions. Small distribution issues are common in molded pulp systems, but significant imbalances leave a distinct record on the woven wire mesh molds. The location, severity, and shape of wear patterns provide clear clues on how the slurry and the vacuum actively behave inside the system. So for zone-specific wear, where certain areas thin faster than others, that frequently corresponds with uneven slurry delivery. When pulp enters the forming zone with high velocity in one direction, fibers repeatedly impact the same region, creating visible hot spots aligned with flow entry points. Vacuum distribution plays an equally vital role. High vacuum zones, which are areas with excessive effective vacuum, experience increased mechanical stress as fibers are pulled aggressively against the mesh, accelerating wire thinning. Then there's the low vacuum zones. Regions with weak vacuum show reduced wear but suffer from poor drainage, fiber buildup, or uneven mat formation. This often prompts operators to increase vacuum elsewhere, inadvertently worsening wear in already stressed areas. Additionally, asymmetric wear across patterned or multi-zone screens highlights unbalanced vacuum manifolds or partial restrictions. The resulting wear patterns mirrors the pressure gradient across the screen, outlining the exact footprint of the uneven vacuum draw. Because these shifts manifest on the mesh before triggering instrumentation alarms, processors can catch developing issues early and adjust manifold design, vacuum zoning, or slurry delivery proactively. Instead of treating your woven wire mesh mold as a passive consumable, operators can use woven wire mesh intentionally as a diagnostic surface. Because it interacts with furnish, water, pressure, and vacuum simultaneously, it serves as an excellent operational feedback mechanism. Effective diagnostics require consistent inspection practices. Comparing screens only at their end of life masks early indicators. Tracking where the wear initiates, how fast it progresses, and whether it remains localized provides crucial context that single point inspections miss. Pairing mesh diagnostics with process adjustments allows for rapid validation. If adjustments are made to vacuum zoning or manifold balance based on wear patterns, subsequent inspections will verify the fix. When wear patterns stabilize or become uniform, the mesh confirms that the root cause, not just the symptom, has been resolved. Ultimately, using mesh as a diagnostic tool shifts maintenance from a reactive to a proactive operation. Screens become measurement surfaces that provide continuous operational feedback without requiring additional instrumentation, contributing directly to long-term process stability. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things Hover and Boker. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.